Thank you very much indeed for that most generous introduction. It was fabulous. Sounds like you're talking about somebody else, but really, it's a great pleasure to be here and a privilege to talk to you all in your homes, in your cities, towns, villages, wherever you are in this time, wherever you're holed up. Thank you very much for having me. So, so I'm now going to share again. Just check that this works okay. So, are you seeing the full screen now? Is it a full screen slide with my mouse on it?
Yes, yes, it is visible.
Okay, great.
Okay, go ahead.
Pardon?
Go ahead. Okay, is it
Go ahead.
okay?
Okay, thanks. So yes, so the topic of my talk today will be imaging, but also including uncertainty analysis. And I'm going to start with an introduction to the general problem to understand why this problem is both difficult and also fascinating, I think. And after we've been through this introduction, then I'll talk through a sort of plan for the next, for today and tomorrow, the topics that I cover. So here is an initial goal for this webinar that I would like to be able to tackle. So I'd like to be able to estimate uncertainty in 3D tomography in reasonable time. And I just want to go through this goal in a little bit more detail. So first of all, I'm interested in 3D tomography because we want to develop methods that can be applied in the real world. So I will be talking about quite a bit about 2D tomography, but at one point I'll show you how that's related to 3D imaging in the Earth. 2D tomography is computationally easier than 3D, but in principle it's very similar. So the goal ultimately is to find algorithms that are efficient enough that we can do this in 3D in the real world. I'm interested in estimating uncertainty. And now let's just first of all define what I mean by that. So I mean that I want to find the family of, in principle, all plausible 3D Earth models. In other words, all Earth models that are consistent with the data that we have recorded, be that seismological or be it geological information that we have. I'm not so interested in the more traditional approach of finding a particular model, let's call it M hat here, which is a best fit to the observations. And there are a number of reasons for that. The first is the kinds of models that we're talking about might be models of the distribution of density or seismic velocity in the Earth or other properties. And these are often, or usually in geophysics, these are continuous properties. So a seismic velocity can be any value, above 0 and, below about, I don't know, 8 kilometers per second, something like that. But it's continuous. It's a continuous variable. And the one thing that we know about any model M hat, which comprises continuous variables, is that the probability that any model M hat is true is identically 0. So no matter which model you estimate, if it's a model consisting of continuous variables, there is 0 possibility that it represents the true Earth. And that's just a mathematical identity that there's no way of getting around. Now, what that means is that we have to understand how far that model can be from the true Earth. And that is part of the uncertainty estimate. The second reason that I'm interested in uncertainty and not interested in this best fit model is that we need to understand the uncertainty in our models in order to combine them with other information to ultimately make decisions. So if we want to combine the geophysical models we create with geological knowledge or with dynamic information from flow measurements or simulations, mechanics, and so on, we have to understand the relative uncertainty in each of these different sources of information to combine them. If one of them is particularly uncertain, then we should give it less weight when we combine them. But unless we've estimated the uncertainty, we can't do that. So as a result, and also for making decisions, we have to have uncertainty if we want to make evidence-based decisions, because again, we need to weight the evidence with its relative certainty, if you like. So that's going to be the goal. I'm interested in doing it in reasonable time because the kinds of applications that we're typically interested in are monitoring seismicity, for example, human-induced seismicity, which then may require some pretty much immediate action to suppress it. We're interested in earthquake and volcano early warning systems, which require immediate decisions to be taken, detecting leaks in subsurface storage reservoirs, tracking pollution fronts, etc. So we want applications that can be, we want algorithms that can be implemented in real or reasonable time. And finally, then, I'm interested in this goal because it's hard. It turns out it's hard, and I'll explain why in a moment. The academic challenge here is worthy of study in itself, because in trying to solve this, we'll develop algorithms that will help in other problems as well. So that's why I think this is a worthy goal, and I'm going to focus on it now for a significant part of this presentation today and tomorrow. So let's now think about a specific scenario where we can start to think about what the issues are. So here is Scotland, a map of Scotland, if you're not familiar with it. And let's say that we were interested in finding out about subsurface structure of Scotland. So imagine that we fired a source up here on the Isle of Skye, and we seismic waves propagated through the crust, and we recorded them at a seismometer down here, which is right on top of my house in Edinburgh. That's where I am today. And we recorded the travel time of that wave, so how long it took to get from the source to the receiver. And let's say we observed that that travel time was 16 seconds. So now what we want to do is to find, excuse me, the family of all the subsurface structures that are consistent with that observation, because any one of them could be true as far as this observation is concerned. So what we typically do is we would parameterize the Earth model into, in my group, we typically use a set of cells. So we sort of split it up into little square cells, sometimes irregular cells. And in each cell, we assign a parameter, which would be typically the slowness of the wave. And slowness is just 1 over the wave speed. The reason we use slowness instead of the speed is just that it has slightly nicer properties in relation to travel times. So in each of these cells, we have a parameter, and which is the slowness. And you can see in the colors there, I haven't given you a scale, but let's say that we have some distribution of slownesses represented by the colors. So we want to know whether this model is consistent with the data. So what we do is we forward model the travel time through this model. So we calculate the travel time. And that might involve, for example, tracing the ray path for the fastest wave. And that's the green path shown here. And once we have that path, we can calculate the travel time along it. And so let's say we do that, and we find that the model has a travel time of 14 seconds. So now we're interested in changing the model, because that's not consistent with the data unless we have very large uncertainties in the data. That's inconsistent. And so now we want to change the model in order to find those that are consistent. There are 255 cells here in this model, and each cell has a slowness parameter. So we have 255 slownesses to vary, and each one of those can vary independently and continuously. And this means that we're looking for an exploration over these 255 parameters to find the models that fit the data. So why is this hard? Well, to explain that, let's first number the cells. So let's say we start numbering the top left and we number them 1, 2, 3, 4, just going across the cells from left across and so on, right through to 255. Now, if we just take the first 3 cells to begin with and just imagine they're continuous, so I can plot them on axes like this. And this model parameter M1 would be the slowness in the first cell, and this one is in the second cell, and this is in the third cell. And so any model I can construct will have some value. It will be a point in this space because this point will be defined by those 3 slownesses. So the model that we just looked at and we calculated the travel time for, it is a point in this space, and here it comes. It's just in front of the arrow there. Hopefully you can see that on the resolution of your screen. It's one point just in front of the arrow. So what we now have to do is we need to explore the rest of this space. And every time we explore, we have to sample that space in some way. So we have to look at other models around in this 3-dimensional room or space or room that's constructed by these 3 axes. And each time we sample a new model, we have to calculate the forward function, the travel time. Now, just to think about this a bit more, just all of us are sitting in a room. So just look at the top left-hand corner of your screen, or your computer, whatever it is you're looking at, and imagine one point right there, just at that corner of the screen. And imagine that in the room you're sitting in, that is the only point at which you know something about the properties of, in this case, the travel time. And that point is infinitely small. Now, what we have to do is explore all the rest of the room, all around you, with these points. Now, if you literally just have a look, you know, up in the corners of your room and down underneath the table that you're sitting at, there is a lot of space in your room to explore with tiny points. And that is quite hard. So we're going to have to take quite a lot of points to really explore that room and to check out all the different locations within it. So if we're to explore these models in these 3 axes on the screen, that's going to take quite a lot of computation. But it's worse than that, because these are just the first 3 cells and the first 3 slownesses. Within that point on the screen, the red point, of course, that is a full model. We saw it on the previous slide. And so there are also values for the cells 4, 5, and 6. And those values lie inside that point. So that point inside it is another room which has values for slownesses in cells 4, cells 5, and 6. And inside that room, we have evaluated one point because it's one model and one set of slownesses. And the difficult thing is that for every single point in our first room, there is another room inside that one for the second set of parameters. And we have to explore that room too. And each point has a different room that we have to explore within it. But it's worse than that, because every single point in the second room, of course, contains a third room with the next 3 parameters. And we have to explore that. And so we have rooms within rooms within rooms, and it carries on until we get to the total number of parameters of 225. Now, this is a disaster. How are we ever to explore this vast space, which, when it's high dimensional like this, and each of these parameters we regard as a dimension, and so we now have a very high dimensional space, the dimensionality, this word here, is high. How are we to explore this space just with points? So, and this problem that when the dimensionality goes up, we need an exponential increase in compute power, or in this case, number of points to explore that space of the same density. That is known as the curse of dimensionality. it's a problem for almost all algorithms, and it is the reason that these problems are hard. What this means is that if we're to progress, we're going to need some very smart algorithms to search this space. We definitely cannot search everywhere. You might want to be interested to know that if we know nothing about these parameters, we literally have to search everywhere. And let's say we search with something like, you know, density of 10 samples per axis. You can't explore more than about 20 dimensions. And that means that every single problem on Earth has ever been solved by exploration, by sampling. If it's really done by blind search, we know nothing, we simply have to explore. All of them have only 20 degrees of freedom or fewer. So this is a real problem. So this is why we need smart algorithms. The plan for the rest of the webinar then, after this introduction, is I want to explore various algorithms, and then I'm going to use them to interrogate, in our case, the Earth's subsurface. But these exactly the same algorithms can be used for medical imaging, they can be used for non-destructive testing, and they can be used for all sorts of other inverse problems. So first of all, I'm going to have a look at a Monte Carlo algorithm, just to explain how that works. And then move on today to talk about another suite of algorithms which are called, well, they come under the general topic of variational inference, and that's really quite different from Monte Carlo type methods. So I'm going to explain what that class of methods is, and I'll look at two in particular. The acronyms will mean nothing to you so far, but we'll explore them, the SVGD and ADBI algorithms. I'll introduce them to you today, hopefully, if we have time. And then tomorrow, what I'm going to do is begin by introducing, you will all have heard of neural networks. I'm going to introduce a particular class of neural networks called invertible neural networks, which have some very nice properties when it comes to assessing uncertainty. But also those particular networks are really useful for another set of variational methods called normalizing flows. So I'm going to introduce those. Now, by that point in the seminar, we will have covered, 4 or 5 different methods. And what we'll find is that those methods, although there is one mathematical solution to an inverse problem or an imaging problem, what we will find is that these methods produce different answers, which is an unfortunate truth we don't often test, we don't like to admit, but it is true that the algorithms themselves produce features in the answers that are not desirable. So what I would ultimately like to do by the end of tomorrow is introduce something called interrogation theory, which allows us to bring together all of these methods together, including the uncertainty and the choice of algorithms, to answer scientific questions about the subsurface. So it's going to combine all the uncertainties from all the methods and all the algorithms into a specific answer for specific questions. And that's where I'd like to get to by the end of the seminar tomorrow. Now on the right, I've just put a list of papers here, and these are just papers from my some of my PhD students from the past and the present. They've done, I've been fortunate enough to have some really outstanding PhD students, and they've done a lot of the work. I'm going to be presenting the methods in general terms, but the examples I show will be from these papers and maybe a couple of others. So a lot of the credit goes to them, and I'll make sure I give them credit as I go through. Any of the papers that come up you can find at my website at the bottom there. Okay, so let's start with Monte Carlo. And I should say that after I get to the end of the Monte Carlo section, we'll have a quick break, and also any questions you'd like to ask before we go on to the final section for today. So for this part, I just want to give special credit to Erica Galetti, who was a PhD student with me about starting, I guess, about 2012, something like that, and stayed during her PhD and then stayed for a postdoc as well, and did a lot of or created the examples that you're certainly going to see in the next few slides. So a lot of credit to her. Now, I understand that or some of the people here today may not be from just a geophysics background. So what I'm going to do is introduce, first of all, the context, so the imaging context that we would be typically dealing with in geophysics. And really this is so that you understand the kinds of data that we're using and where they come from. So, and I'll be using similar data throughout most of the talk. So here's the UK, Scotland at the top there. And I'm going to be studying, some of the examples I use will be from this area, partly because it's close to home, but partly also because it's a relatively small island. And that means it's surrounded by oceans, and the ocean itself is constantly pounding the shore with waves, but also the slopes of the continental shelf are being pounded with low frequency swell. And what that means is that as that impact happens, that generates seismic energy, which propagates through the interior of the Earth across the UK. And so we have energy coming in from the Atlantic, and then from the North Sea and the English Channel at the bottom. And this is happening constantly. So we constantly have what we call ambient waves, or background seismic waves, propagating through the interior of the UK. And that's the energy that we're going to use, that we use quite commonly now in seismology to image the Earth. So we have a network of seismometers. These aren't the real locations, I'll show you those in a minute, but these seismometers are constantly recording these waves as they go through, and that's going to give us records of what we're going to call ambient noise, ambient seismic noise. Now, the way that we use these is we record the noise, and then we take pairs of those recordings and cross-correlate them. So for example, I could take this station here, roughly in the middle, and this one up here in the north. I take long records, so for example, a month or even a year of that noise, and I cross-correlate it. And the result that comes out is, we can show theoretically, is an approximation to the seismogram that I would record at the top seismometer if the bottom seismometer had actually been a source, a relatively impulsive source, and had fired. Now that source never existed, but I can still get the seismogram at this seismometer as though it had actually fired. And that's what ambient noise, this method is called ambient noise interferometry. So that's where we get our seismograms from, and that's how we make sense of all this background noise that's coming in. And we can do this between all pairs of stations, and so essentially we in turn convert each seismic station into a virtual or imagined source of energy, which was recorded at all the others, and we obtain the seismograms. Now, from those seismograms, we can pick the travel times of the waves, because we know when the source occurred at time 0, then and we see a wave coming in at time t, well, we can pick that, and that gives us the time it took for the wave to travel between these station locations. And we'd like to use those data to solve for the subsurface velocity model. And so we're going to end up solving equations like this, where the travel times of the data and the velocity model is the m here, that's going to represent the model that we'd like to find. And the important point about this is that we've recorded the data. We're trying to find the family of models that fit the data, so all the different models for which they are related, such that if we apply what's called the forward function, g, which converts the models to data or translates into the corresponding data, we'd like to find all the models which match the observed data. And the important point is that g is nonlinear. it is, and often very nonlinear. So let's have a look at some real data. So here is the actual station distribution for the UK in various years. And so in turn, what we do is we take pairs of these stations and we cross-correlate them. And so we'll convert, say, that station there into a virtual source. And we will construct estimates of the seismograms at other stations. So for example, that one, that's the Edinburgh station again up there. And then we'll do this for all the different stations and just carry on through until we've got recordings of that source at all of those different stations. And then we can just line those virtual source recordings. These are the actual estimates of seismograms that we get out from this virtual source. And what you can see is we've lined these up with distance from the source. So we've ordered them by the distance away. And so we can see this arrival carrying on down through the data. And this is a surface wave. It's traveling across the surface of the Earth, but it's vibrating as it travels laterally across the Earth. It's vibrating down into the Earth. And so it's sensitive to subsurface properties, as we'll see. This is the wave that we pick using a variety of different methods. We pick the travel time of that, and that is the data that we want to use for tomographic imaging. So that's the setup. Now let's talk about the first of the inversion methods that are going to do this imaging, and that's going to be a Markov chain Monte Carlo method. So it's called the reversible jump Markov chain Monte Carlo. That's RJMC. Reversible jump Markov chain Monte Carlo. The class of methods is the Monte Carlo suite of methods, and these are stochastic or statistical sampling methods. They generate samples from a probability distribution that represents the solution, and I'll let's explain that. This probability distribution is given by Bayes' theorem, and this is Bayes' theorem is this equation down here. The one on the left is the key probability distribution for us because it describes the solution to our problem. If I just read it out, this P here stands for the probability. And this left-hand term is the probability that any particular model M is true, given, that's the vertical line, given that we've observed a particular data vector D obs. So, and this is exactly what we want to know to characterize our uncertainty. Given we've measured these data, what is the probability that any particular model M is true? So this probability distribution describes that uncertainty. And we call this the posterior probability density function because it's posterior means after, it's after we've recorded the data. Now what Bayes' theorem says is this depends on three terms on the right-hand side. The first one is called likelihood, and it turns the thing around on its head and says, well, okay, if we want to know how probable M is of being true, let's assume M was true. What's the probability that we would have observed that data? If actually there's a very little chance we would have observed this data if M was true, well, it's quite unlikely that M is true. So the likelihood describes essentially the data fit of the model. The second term on the right is called the prior distribution, and that is a distribution which only depends on M. In other words, it doesn't depend on the data at all. And this describes all the information that we had about the model before we started the inversion, before or without the data, let's say. That's why it's called the prior. And then on the bottom, we've got a term that we call the evidence. And the important thing about the evidence, there are two important things about the evidence, actually. The first is it doesn't depend on the model at all. And so if we we have a chance to develop algorithms that don't require us to use this term because it's not telling us about the model. The second thing that's important about this term is it's very expensive to calculate. In fact, because this on the left is a probability distribution, it has the property that the integral of this distribution over all models must equal 1. And this term on the bottom here is the normalizing factor that makes sure that that's true. In other words, to calculate it, we have to integrate this over all models, and that's extremely expensive. So we would like to avoid ever having to calculate the evidence if we could. And this is where the reversible jump Markov chain Monte Carlo algorithm comes in, because we never have to deal with the evidence. And I'm going to explain to you now how this works. We start with an initial model M, and in our case, remember these models are describing the velocity structure in the Earth, and I'm going to parameterize, in this case, I'm going to parameterize the models like this. So it looks a bit odd. So in the background there you can see the UK, and then you can see over the top this mosaic of oddly shaped cells. These are called Voronoi cells, and they're defined by these little black points in the middle. And essentially the cell surrounding, for example, this node or center, they're sometimes called, the cell that surrounds it, or the patch, is all points that are closest to that point and to any of those other points. If any point in space is closer to that point, then it's part of its Voronoi cell. And the nice thing about Voronoi cells is they fill space exactly. And I can change the Voronoi cells just by moving or removing or adding nodes, these central points. So it's a very flexible parameterization. And that's important because in this Monte Carlo, I'm going to allow the parameterization to vary. So we start with this initial model, and the model that consists of these cells, I should say that the color in here corresponds to the velocity, so the speed of the wave traveling through that cell. Now, what we then do is we evaluate the travel times for this particular initial model. So we do that by calculating the ray path and the travel times. Here are the ray paths, these are the shortest paths between all the stations. We calculate the travel times on the rays, and then we know at that point how well this particular data fits the observed data. This particular model, sorry, fits the observed data. What we next do is propose a new model, M dash, so another one. And we're going to do this in two different ways. And we're going to do this many times, I should say, iteratively. And we're going to, each time, we're going to do it in different ways. So if we're at an odd iteration, iteration 1, 3, 5, we're going to just choose at random one of these cells in the model, and we're going to change its velocity, or we might change one of the uncertainties on the data, because we're also including them in the inversion here. If we're at an even iteration, we're going to move we choose a cell at random and move its center, or delete the cell, or we might add a new cell by just simply adding another center or node into the grid. So we're going to change the model parameterization on even iterations. On odd iterations, we're going to change the velocities or the uncertainties. So let's focus on, for example, let's say we were on iteration number 1. It's an odd iteration, so we're going to change the velocity of that cell, shown in yellow, and randomly we assign a new velocity to it. It's gone from blue to red, so quite an extreme change. And we got a new model. Now, in the next step, we calculate the travel times for that model, which gives us the data fit for that model, if you like. And now we compare these two models. This is a Monte Carlo method, but it's also a Markov chain. That first MC stands for Markov chain. It's a chain of models. In other words, we're going to step through model space. And we've got to decide now, do we like this step from this model to this one or not? And we do that using what's called an acceptance ratio, which is actually a probability that we should accept the new model or not. I'm going to explain what that is in a moment, but let's say that we decide not to accept it. If we reject the model, then we just simply delete it. We stay where we are at the initial model, and we go back to the top and propose another new model. If, on the other hand, we accept the new model, that new model becomes our new current model. So we take that step, and now we go back to the beginning and propose another new model, the next one in the chain. So it's a very easy algorithm. The only important part is this acceptance ratio, alpha. And it looks something like this. And you can see that it's the ratio of the prior probabilities of the two models, m dashed and m, the likelihoods of the two models, m dashed and m, and also this Q here is what's called the sampling distribution or the proposal distribution. So it's how we chose the new model. And the J here just deals with changes in volume if we, in model space, if we delete or add cells. Now, I'm not going to prove any of this to you, but this particular form has two very nice properties. Firstly, it promotes natural parsimony, which means carrying on, iterating through this algorithm, we will tend to accept models that only have a sufficient number of parameters to explain the data. This algorithm doesn't, or shouldn't, if it's working properly, it shouldn't add in more and more parameters to fit the data better and better. It should only fit the data up to the extent where that their uncertainties justify. And the second thing is that if we iterate, and just carry on iterating to very large numbers of samples, in principle to infinity, it ensures that those samples become distributed according to the Bayesian posterior probability. And remember, that's what we're trying to find here. And so this is an algorithm where none of these terms involve the evidence, you'll notice. So we don't have to calculate the evidence. We can just iterate through it, calculate samples, and then work out how densely distributed they are, because that is what represents our solution, the posterior probability density function. So let's see some of the results of this for the UK case. So all of the models look like this, and this obviously isn't very geological. It's not very easy to interpret. So what we're going to do, and there are going to be lots and lots of models like this, all different. So what we're going to do to help interpret them is we're going to overlay with a grid of points, these green points, and we're going to look through the family of all the models, and beneath each particular point, so let's focus on one, perhaps we focus on this one up here in the top left, in the red cell. We focus on that point, and for all the models, we observe how the velocity of the model changes beneath that point. And that distribution of wave speeds, if you like, in all the models represents the uncertainty on the velocity at that point. So let's just do that. If you focus on that cell, sorry, that point a moment, and we just page through a few of the models, and you can see the velocity changing from low to high to intermediate to low to high, and we just continually watch that cell, and eventually, when we've gone through all of our samples, we can calculate the average velocity at that cell. And it comes out as white, which is just over 3 kilometers per second. And we do that for every single point, and then we can contour, or just shade, interpolate this map underneath, which is the average velocities that we find at every point. Now, this is just the mean or the average velocity model, but of course, as we went through, we got a whole range of velocities at each point, so we can also calculate some sort of measure of uncertainty at that point. So we could look at the whole distribution, which is called the marginal distribution of those velocities, or we could just calculate a statistic like the standard deviation of those points. So if we do the latter and we calculate the standard deviation of the velocities at every point, we get a map of standard deviations. And this is just a characterization of our uncertainties. So we put these two maps side by side, the mean or average on the left and the standard deviation or uncertainty on the right. And we just have a look, first of all, at the mean map. We can see some features which give us some confidence here. So we can see the Midland Valley. So I live in Edinburgh here, Glasgow's there, and this valley is full of sediments. And so we see a slightly lower velocity there, which is good. That's what we would expect. We can also see this deep low velocity in the Irish Sea basin, and we're going to look at that one in detail later. And deep low velocities around London basins, and they're very deep basins there. In addition, we can see the bedrock of the Scottish Highlands, the southern uplands of Scotland, the Pennines in England, the granites in Wales, and the granites in Cornwall. And so these are geological features that we would expect to see, and so seeing them gives us confidence in the algorithm. Now let's have a look at the standard deviation, or the uncertainty map, over on the right. And what we see are some strange or interesting patterns. In particular, we see this circular feature standing up here, this loop-like feature of high uncertainty. So it's low uncertainty in the middle high uncertainties. And if we look over at the mean map, we see that that loop is surrounding this low velocity anomaly over here. Now, this was a bit of a mystery when we first saw them. We didn't really understand what this was. So we tried taking the same data set and inverting it using another algorithm, which was purely linear. So it basically approximated the forward physics with a linearized version, and we estimated the uncertainty using it. And I'm going to put the uncertainty over on the left here. That's what we got, the linear algorithm, loops. So this means that these loops are definitely a consequence of the non-linearity in the problem. So what could that be? Let's just have a look at that loop in particular. Let's expand it out. And we're going to look at 3 points in the loop. So the 3 points down here. So first of all, let's look at the point in the center of that loop in orange. Now, remember that when we looked through all of our models, we got the full distribution of the velocities beneath that point. And so we can now look at those. It's called the marginal distribution. It's just a histogram of the velocities that we observed in that beneath that point. And we can see that they're all very low velocities, quite narrow distribution. And it means that we've got quite a tight bound on the velocity. It's around to maybe 1.8, something like that, kilometers per second. And so that's why at that point, we've got quite a low uncertainty. And it's in a basin, which is why we have a low velocity. And now let's look at this magenta point over here on the left. This is in the high uncertainty loop, and it's on the boundary of that basin structure that's here. So there's a basin here and out here, not a basin, or not at this particular point. And when we look at the marginal distribution for that point, the distribution of velocities, we see that it's got 2 peaks, it's multimodal. We still see that same peak as we saw at the interior of the basin, but now a second peak has emerged. And this second peak is the velocity that's external to the basin. And so what we see is that that point is potentially either inside the basin or outside the basin. And this distribution tells us that we don't really know which. It seems a bit more probable that it's inside because we've got a higher distribution there, but it might be outside. So what's actually happening there is that in all the different models for different Voronoi cells, some of the cells of the basin extended out here, where my mouse is, and so the magenta point was inside the basin. Whereas in other models, the basin only extended out to here, and so the magenta cell was outside the basin. And those 2 cases would create these 2 peaks in the velocity. So what that means is those 2 peaks are representative of the fact that we don't know where the boundary of the basin is. Now that's a hypothesis. Let's check it over at this other point on the other side, the green point. And again, we see exactly the same behavior. 2 peaks, the velocity inside the basin and outside the basin. And again, by looking at the models, you can see it's because sometimes it lies outside and sometimes it lies inside the basin. So what this means is that the loop is telling us about the uncertainty in the boundary of the basin structure. And what's interesting about this is that when you get your eye in, you realize that the whole uncertainty map consists of loops. We've got that one we've been looking at now, but look, there's a loop down here. There's another loop here. Both of those are surrounding low velocities. And we've got a very thin loop down here around another basin. Around this part here, we have a loop around a high velocity zone. The whole map consists of loops, and indeed that's showing us the uncertainty and the location of these low velocity anomalies. Largest loop of all is this one right around the outside. And that's telling us that although we know something about for example, up in Scotland, we can see that the velocity up here is really quite fast, and then it goes slow, and then it goes fast again. So we've got low uncertainty up there for lots of stations. Because the data is mainly on land, we don't know how far that extends offshore, and so we don't know the boundary. And that's why we have high uncertainty all the way to the edge of the model, because we simply have no data out there. And so we get an uncertainty. To summarize that, the uncertainty seems to comprise loop topologies. They're definitely formed by a higher order physics, not the linear physics, because they're not observable using linearized tomography. What's more, while I gave you a number of reasons why I'm interested in uncertainty at the beginning of the talk, in fact, the loops themselves are useful. They're an interpretation tool. We can use, they describe the uncertainty in the, first of all, they encircle the velocity anomalies, but they also describe the uncertainty in the shape. And so really, these are a fully non-linear measure of the spatial resolution of our structures. What's also nice about them is we understand them intuitively as well as quantitatively. And so we expect to see loops around our structures. If we don't see loops around them, then at the very least, we have to examine whether the algorithm is working. And so we're going to use these loops in part as a bit of a diagnostic tool to evaluate other algorithms. Okay, so we've looked at the uncertainties, we've looked at Monte Carlo, and we've now found the speed with which surface waves travel across the Earth. I just want to link this up to the 3D imaging that I promised at the beginning. For the rest of the talk, we're really going to focus on 2D images of the surface waves, but the reason is that we can use these to construct a 3D image. The reason is that the surface waves oscillate as they travel, and this particular map was for a surface wave oscillating with a period of about 10 seconds. So 10 seconds to oscillate one way and then the other, up or down or left or right as it propagates. As waves take longer to oscillate, they oscillate deeper in the Earth, and so they're sensitive to deeper structures in the Earth. And conversely, if we look at high frequency or more rapidly oscillating waves, they're telling us about shallower structures. So if we look at the wave speed maps across different periods of oscillation, we can use those in a second step to infer the velocity structure of the Earth with depths in the Earth. I'm not going to go into that step in any detail, but essentially we also can use exactly the same algorithms to do that second step. So, for example, in this case, in the UK, this is the 10-second period map, but I can construct those mean velocity maps at a range of different periods. Here we have 4 seconds period for oscillation, and this you can see the waves travel relatively slowly, so red structures coming up, compared to if I do tomography with a 15-second oscillation, so very slowly oscillating waves, we get much faster velocities. And that's because they're sensitive to deeper structures, which tends to be faster. Of course, with each of these maps comes an uncertainty map, and here we get exactly the same thing. There's the map in 10 seconds that we were looking at previously, but you can see that you get uncertainties for all the others. And the combined set of these two sets of maps, we can now invert the structure of depth beneath the UK. So let's just have a look at one particular area. I'll just look at the results. This is the Irish Sea Basin. And here is the structure, a cross-section of the structure at 1 kilometer's depth. And you can see these low velocity sediments in the basin, surrounded by higher velocities like here. And so here on the right is the uncertainty standard deviation. A bit higher in the basin, a bit lower over here and here, but anyway. And now we can step down in depth, so 2 kilometers depth, very similar structures, 3 kilometers, 4 kilometers. And as we get to 5 kilometers, we start to get to the base of the basin. The sediment disappears and we start to see the basement rock. At the same time, the uncertainty starts to increase. And as we go out of the basin, 7, 8, 9, 10 kilometers, we're now fully out of the basin, and the uncertainty actually starts to get high inside the basin or beneath the basins. But this just shows you that by imaging in 2D, we can use the results to construct 3D images. And that's the ultimate goal of all this. And the nice thing is that by translating the uncertainties properly, we get uncertainties in those 3D images as shown on the right here. That's what we're after. So that's the first section of the talk on Monte Carlo methods. And perhaps at this point, I suggest that we could, if there are any questions, I'm very happy to take questions now. And then I suggest we have a short break so we can get a cup of tea or whatever before we go on to the second section for today. Salman, I don't know how you want to manage the questions.
Yes, students, you have any questions you can put in the chat box, or I can narrate that what are the things can be addressed.
Unfortunately, I can't actually see the chat when I'm in this presentation mode, Salman. So maybe you'll have to read them out.
Okay. If they put in the chat box, I can read, or directly you can also discuss. Sir, how was 3D tomography performed for surface waves? Is it equinal based tomography? That is the one question asked by students. Sir, how was 3D tomography performed for surface waves? Is it equinal based tomography?
Right, yeah. Actually, I've now managed to see the chat, so that's great. Thanks for that question. So the 2D tomography, so constructing the surface wave maps, was using essentially what's called a fast marching method to calculate travel times through those through the various models that we considered. So all those different models with Voronoi cells, we could calculate the travel times, which using a fast marching method, which essentially marches the wavefront out from any source across the model. And that's really what it's doing, is solving the iconal equation in 2D. For the third dimension, what we do is we take the velocity measurements across the whole set of maps, and they become our data. And so we do exactly the same process. For example, you could do it with the Monte Carlo method again, but this time sampling 3D models. And for each 3D structure, we compare them to the set of 2D surface wave velocity maps. And we calculate the velocities using a modal approximation for the surface wave dispersion. So it's a two-step process. In the first one, we're using an iconal solver, essentially. And in the second one, we're using a modal approximation, a modal model, which calculates the speed of different surface wave modes for a 3D structure. I hope that answers the question.
Okay, next questions, Vivek. Vivek, can you have that questions you can directly ask?
Okay, thank you, sir. Thank you, sir. Yeah. So, hi, Andrew. Thank you for giving this very nice.
Just switch on your video, because it is difficult, because when you are putting on questions, you just please switch on the video.
Okay. I think, yeah. So thank you, Andrew, for this wonderful talk. You have talked about reversible jump algorithm and how uncertainties are estimated. So my question is about prior, particularly the width of the prior. So if we keep on increasing the width of the prior, the posterior will get broader. And because of that, the uncertainty, the standard deviation will start to increase. So your uncertainty is a function of width of the prior. So how robust are we in case of Bayesian inversion about uncertainty if it is a function of prior width? Thank you.
That's a very good question. So what's interesting about Bayes' rule, if you remember that equation for Bayes' rule, it's got two terms. It's got the prior term, and that's multiplied by the data fit term, the likelihood. And you know, that's really quite an interesting combination, because it means that the prior has exactly equal mathematical weight to the data. So the prior is equally important. And so actually right now, you know, quite a bit of the work we're doing is on the prior to try to get better prior information in there for exactly the reason that you're saying. Because a lot of the time we have to use, I mean, our priors are very weak. So essentially we know velocity is positive, and we know that if we're using surface waves that are oscillating at, you know, periods of greater than a second, they're probably going to be above 1 kilometer, maybe down to 0.5 kilometer per second speed. And so we tend to put a lower limit on that, and nobody's ever seen a surface wave of that period going faster than 8, so there's an upper limit. And in between, we just we use a uniform prior or something else to sort of focus information, or to represent our information that we have. But that is, and so I think that's okay, because we do know that there are these bounds on the velocities, but it's really not very tight. And I think what's important about prior information is just that it has an equal influence to the data. And so it makes a huge difference focusing on the priors. So it's a very good question. Thanks.
So following to that is one of the reviewer actually asked me this type of question. So for example, the tomography model that you were showing. So sometime if you are using a broad uniform prior, the perturbation in your mean velocity model, let's say if it is 10%, then in case of your uncertainty, your velocity can go 50%. So your uncertainty, standard deviation is showing more deviation, more perturbation compared to your mean velocity that is shown at a particular period. So how, that was the question, but I get that this actually represents the uncertainty. So my just last question is, should we always use a standard deviation as a measure of uncertainty? Or any other measure to?
No, we don't always use standard deviation. So there's another very good one that I'm going to talk about tomorrow is entropy. And that is actually a much better one because it's related to information that's contained in the data. But standard deviation is a nice one in some ways because it's well understood and it gives us a nice visual representation. But to come back to your first point, it isn't automatic that as you expand the width of the prior, the uncertainty gets larger in the solution. I mean, that's only true in areas of the model that aren't constrained by the data. So if you have an area that's well constrained by the data, expanding the prior doesn't do much to the uncertainties. And so really the prior has most effect in areas that are really under constrained. And that's how it should be, right? I mean, where we have no constraint from the data, we should see the prior. Yeah.
Thank you.
Welcome. Okay, a bunch of questions, great. Simon, do you want to manage or shall I just jump in? What would you?
Another questions, one of our students, Shamin, she speaks that whether, sir, you have any GitHub code so that we can use in our work. GitHub repository.
Yeah, so some of our codes are on GitHub, some of them are not, but most of the codes, we have a version that we can give. So if you look at the website, so you've seen maybe at the very start of my talk, I'll put the slides up again in a minute, there was something called the Interrogating project, and that is a consortium project. So it's a funded project with a few PhD students on it. If you look at the website for the Edinburgh Imaging Project, and you can get it off my website too, you'll see that there is a section there for codes, and quite a few of the codes are freely available there for you. The ones that aren't there, just contact me or contact the author, the student, and ask if you can have a copy. Some of the codes we're not allowed to give away because they were funded by industry and they haven't yet been released. As a public. We hope that they will be soon, but most of the codes we can give you a version if you just ask, or it's already there on the web page. Some of those are on GitHub, some of them are not. And but if you look at the Edinburgh Imaging Project page, you can see what's available. So I see there's a question on the sensitivity. Yes, the question is, can you comment on the sensitivity of the initial model for Markov chains? Sorry, Simon, do you want me just to wire into the questions? Is that okay?
Just I'm reading that question.
Yeah. So there's a question from I don't know how to pronounce it. Breach? How do I pronounce it?
From Breach Bhushan Singh has asked us, can you please comment on the sensitivity of the initial model used in case of Markov chain Monte Carlo or reversible jump Markov chain Monte Carlo? That is the question.
So there is a sensitivity, and so when we run those, I didn't mention the details of how we run it, but we usually run the chains for many thousands of iterations first before we take any samples out that we actually use to interpret. These chains were run actually for millions of samples in this case, and I think the first few 100,000 we just discarded. And then after that, we took every 100th model, so that, you know, subsequent models had lots of models in between to try to uncorrelate them a bit. So good question. I skimmed over that bit.
Another questions by Gautami that, hello sir, would you please comment on the advantage of Jacobian in acceptance ratio?
Yeah, that Jacobian is really just there in principle, because if the Monte Carlo method itself is choosing the number of cells to use, and these can vary from, you know, some of the models go down to just 15, 20 cells, and others go up to 200 cells for the UK case. Now, as we saw in the very start of the talk in the introduction, if I have 15 cells, I've got sort of 50 or 5 rooms within rooms within rooms. 5 layers of that gives me 15 parameters. But if I've got 200 parameters, well, I'm in that terrible situation that I described at the beginning. And that's because the volume increases in principle. The Jacobian is there to take care of that. Now, there is an odd property of these particular Jacobians in this particular application. They all turn out to be to give a determinant of 1. And it's just a particularly nice property in this case, but it's not always the case. And so the Jacobian is there so that when we compare a model with 15 dimensions with a model with 16 dimensions, we are fair about, you know, the fact that the 16-dimensional model has more freedom to fit the data. So it should have to fit it better in order to be preferred over the 15-dimensional one. So it's sort of intuitively, it's kind of fairness criterion, and it evens it up. But in this case, it turns out the Jacobians end up being just identity matrices or having determinant 1.
So another question is from Jaswant Soni. Did you retrieve lab waves from ambient seismic noise? How important is consideration of source directionality and distributions in retrieval of lab waves from ambient noise?
Yeah, so actually what I just showed you was love wave analysis. So I should mention, I think that one was love waves that I just showed you the maps of. We've used Rayleigh waves and love waves for this. Remember that the sources that we're using here are virtual sources. So they're not actual earthquakes, they're constructed from ambient noise. So the source directionality is a bit of a difficult concept with ambient noise sources. It varies depending on the noise source distribution. Now, ideally, if you wait long enough and you process the data carefully, as we try to do, you end up with a source that is directionless, or it's isotropic, I should say. And so then you don't have to worry about this. But clearly then the seismograms, what you do have to do is align the seismograms so that, you know, the two components, the horizontal components of the seismograms, align them so that you are looking at the transverse oscillation to give you the love waves rather than inline oscillation, which would be Rayleigh waves. So that rotation you have to do, but you don't have to worry so much about source directionality. So I guess that's all the questions.
I think there is there any other questions from students? Otherwise, we can take some break and then the next session may continue after. from student side, if you have any few questions, we can 1-2 questions we can take. Otherwise, we can have how much breaks we can take? 5 minutes, 10 minutes.
Now a couple of questions just come up.
Sir, what
is
is
there
the
any-
research scope for seismic inversions for 3D model by deep learning?
Yes, and we'll see some of that tomorrow. And I guess you need to ask Salman here. He's he's one of the experts too. So yeah, definitely there is scope for that.
So that is a very relevant questions because that some of the works Professor Katic already has done in the past and will be doing in the future. I hope that that computational part, how we can bypass using that by neural network training, some of the computational thing. I think 3D models, they will have that much more number of parameters to be optimized and much more amount of these things has to be controlled. So in that case, this deep learning can be a potential, I think, alternative for bypassing some of the tomography image computational part, where these inversion solutions can be memorized or keep in some places, so that in the subsequent iterations or subsequent calculations directly that type of informations may be used without again recomputing the forward calculation, etc. So that is the one aspect. And second aspect is that the uncertainty in the 3D means deep learning, it is one of the fascinating things where this whether we can address all sort of uncertainty at every stage in the tomography problems. So I think that much requires that sincerity and dedication from young generations that can take the challenge and solve this type of problems. I think Andrew can add more on that because he has a strong mathematical background to address.
I mean, no, I agree with everything you've said. So yeah, I mean, it's problematic if you want to learn, you know, to invert for the full 3D model at once. That's going to be hard. It's again, the curse of dimensionality affects the training of the neural networks, and just as much as it does any other method. But so what we have to do is be smart about splitting it up into manageable portions in some way, using the physics to help us do that. And so, for example, what I just showed you, the stage of going from the surface wave phase velocity maps to the depth inversion, if we do that point by point, I'll show you tomorrow, just training a network, an invertible neural network to do that for the depth inversion. And then you essentially run it point by point for about 100,000 different points. And that's what gives you your 3D model. And what you've done is then you've split up the 3D inversion into lots and lots of 1D things, each of which is easy to train, or relatively easy to train the network for. So, and then the whole full 3D inversion takes you know, minutes rather than months.
That is a very good, nice point, because some of the limitations are there. This curse of dimensionality is a very common phenomenon in these inverse solutions or the inverse mapping. But there is a crazy things are going on around that, whether the whole routine of these inversions can be replaced by the automated things or AI. That is, some of the papers or research articles are coming up in that lines, that data driven means the full automations, whether we are going for in that directions or no. I think tomorrow's lectures will be more fascinating, touching this machine learnings and beyond, whether can we replace this whole immersion theory by this deep learning or machine learning algorithms. That is the questions where people are being asking everywhere, from the classroom to everywhere. That
yeah, I'm a little bit skeptical about that, because just because I mean, there isn't a way to get around the cursor dimensionality so far unless we regularize the problem in some way. So we put in extra information to help us to basically limit the amount of the parameter space we have to explore. Because the problem with training networks is that, you know, we tend to have to train them across much of the parameter space, otherwise they won't work across much of the parameter space, and that means exploring it. Anyway, I mean, there are ways to deal with this, and we'll see tomorrow when we get to the normalizing flows part. We'll see how to use networks to do a much more limited search, but to help us to explore specific parts of the parameter space. I think that might be useful. But yeah, hopefully we'll get to that then.
So one question quickly, there is a question from Jyotima. So what should be the maximum and minimum limits between station spacing for this reversible jump Markov chain Monte Carlo ambient noise tomography? One more question is, what are the possibility for joint inversions of travel time, body wave, and ambient noise tomography?
Yeah, so there's no minimum and maximum station spacing, except it depends. Well, sorry. If you mean minimum maximum due to the ambient noise, then that is there is a limit there. So we typically we're not successful with ambient noise travel time estimation, let's say, when the station spacing is less than about 3 wavelengths. So whatever the dominant period is of the noise, we tend to get much better results when the stations are further apart than 3 wavelengths. And there are some good theoretical reasons why that should be so. On your second part, could we do joint ambient noise and body wave travel time? Yes. So in fact, we have a code that is available if you want to use it, which does full 3D Monte Carlo directly from the surface wave dispersion of ambient noise, along with local body wave tomography from local earthquakes. And so we've used that for things like trying to get the velocity structure around some kind of anthropogenically activated seismicity, like around a mine or some kind of injection through fracking. The project is starting trying to use that around subduction zones. So, so yes, we definitely can use that. They use it jointly.
So there is another question that what criteria should be considered for Green's functions convergence for retrieval of lab waves?
Yeah, I mean, this kind of question is quite hard to answer because it really depends on the distribution of your noise sources, how well ambient noise interferometry works. That's for sure, and particularly with love waves, it's more difficult than for radio waves, typically at least. So essentially what we do is, that's all I can tell you, what we do is we will use a certain range of lengths of records. So we might consider 1 month of noise, a week of noise, a day of noise, 6 months of noise, and we will essentially use the length of time which adding further noise doesn't change the results. So we just expand the range of noise until we've got something that isn't changing. And that's what we do. I'm not sure that I know of a way to specify any better criterion than that. I mean, of course, you have to do some kind of processing to the noise. I mean, you have to bandpass it at the very least, and essentially, depending on how you cross-correlate it, which there are a number of different methods, you can sort of weight different components of the noise, and you can window the noise around particular arrivals. There are lots of tricks that some people use. We tend to do very basic processing, really minimal processing. We simply bandpass it and cross-correlate it, and perhaps with some normalization, that's all.
Okay, we can take one break now. For how much? And then after that, we can start 5 minutes or 10 minutes.
Sure. Whatever you
So
prefer.
we will start again at, now it is how much time? After 10 minutes, we will start. That is okay?
It's absolutely fine for me. What would you like to do though? Because the overall time limit is going to be up. I mean, I'm not going to get through. Put it this way: I'm not going to get through the next presentation in the time in the quarter of an hour that's left after the break. So, would you like me to? What I can do in the break is I can sort of take out quite a few of the slides and simply just get something to fit in. That's probably best, isn't it?
Yes, yes. As you convenient you do, because the question answer is important because students are attending. So we can skip some of the slides, but question answer is important because student point of view, it is important.
So sticking to the final time is important for the students. Is that what you mean? Yes.
You can skip some of the slides of the second.
No, I will.
Second talk.
Yeah.
And we will meet, I think after 10 minutes, we will start and you can, for half an hour, I think it is okay. For 30
Okay,
minutes.
no, great. Thank you very much. Great. See you then.
So now we have 10 minutes break. So we will start at 6 again. Resume the second part of the talk.
So, Salman, should I share
Yes,
my
you
slides
can
again?
start, and at the end, if any questions are there, then we can take.
Yeah. Okay. So you can see the slide and you can see my mouse?
Yes.
Yeah, great. Okay. So what I've done just in the coffee break there is it's good news for anyone out there who doesn't like maths, because I've deleted quite a lot of the maths from the next section, just so that we can get through it in reasonable time. And I can still give you a flavor of the first of these two variational methods. Like, you know, this talk was really about uncertainty assessment using Monte Carlo and machine learning methods. And it might look, you know, when one thinks of machine learning, one tends to think of neural networks, typically. But actually, all of these methods, so the two variational methods shown here and the other one down the bottom, normalizing flows, all of them have come out of machine learning communities. One or two of them were around before really machine learning took off again in its current sort of trend. But nevertheless, the machine learning community has really developed these. And so this is all machine learning from now on. So let's have a look at variational inference, because this is a different way, to solve inverse problems, the same inverse problems, without using the Monte Carlo methods that I just described. And here I'd like to give particular attention or credit to Xin Jiang, who again was a PhD student in my group and is now still a postdoc, who's been very influential and productive in developing these methods. And this was following actually on from a previous PhD by Atif Nawaz, who finished a few years back. I should have had him up here as well on this slide. Yeah, great input from them, and a lot of the figures that you're going to see are created by Xin. So what is different about variational methods is that they allow us the opportunity to estimate these probability distributions that we're interested in, the uncertainty distributions, using optimization rather than random sampling. So again, excuse me, still trying to find the family of all the plausible Earth models, but rather than relying on Monte Carlo, which again is this exploration of space just through sampling, in variational inference we take a slightly different approach, which allows us to use optimization methods. So in this bit of the talk, I'm going to introduce these two variational methods and apply them to travel time tomography with and we'll see a real data example there to a small array. I do actually then at the end have a separate section applying it to full waveform inversion problems, but I think I'll probably have to cut that out just in the interest of time. But if you're interested in either of these, you can see these references on the side of the page. I can direct you to them later if you miss them. So we're trying to find an estimate of the posterior distribution still. And in order to represent, to be able to find this estimate of the posterior distribution, which is the left-hand one here, the probability model given the data, using optimization, we have to have a different strategy. And there are two strategies that we're going to see today. The first one is that we try to fit some sort of semi-analytic functions to P. I mean, P is a function, it's a distribution, but it's a function of n. And so we could fit some other functions to P to try to represent it. So for example, we could choose a family of functions, let's call them Q, and so one possibility might be Q would be the family of all Gaussian distributions. And those Gaussians are going to be defined by some parameters. Here, psi, so these would be, for example, the mean and the covariance of the Gaussian. And what we could do is we could choose those parameters so that we find the particular Gaussian which is as close as possible to the posterior distribution. And in that way, this is an optimization problem because we can essentially optimize the fit of Q to P. So graphically, what's going on here is we've got some posterior distribution P, and we don't know what it is. So although I've drawn it here, we don't know what the shape of that thing is. And the way this would work schematically is we would start with an initial estimate of Q. So this is the function we're going to fit to P. So it's just some Gaussian somewhere, and maybe we center using our prior information. And then what we do is we've got these two parameters, in this case labeled as phi1 and phi2, so the mean and the variance of standard deviation. And we work out how to change those parameters in order to better fit P. So we'll use a few samples of P just to calculate gradients of the misfit between the two with respect to these two parameters. And so we'll find that if we move the mean to the right, it's given by that arrow, and if we decrease the standard deviation, then the function is going to get closer to P. And we'll just move it a small step in that direction. And then again, we will take another iteration. So we've still got to move the mean, and we've still got to reduce the standard deviation. Our distribution is still too wide, and we'll move it a little bit more. We keep iterating and iterating until we find an optimal approximation to the posterior within our family of whatever we've allowed. So in this case, we've allowed Gaussians, so this is what we get a Gaussian. But in general, we could use much more flexible functions than just Gaussians to fit the distribution. And in fact, the first method, ADVI, which stands for automatic differential variational inference, a bit of a mouthful, that's why we just say ADVI, does in fact just use Gaussians. It does almost exactly what you're seeing there. I was going to go into the sort of mathematical details of each of these algorithms, the two, but in fact, I'm just going to show you them graphically like this. I'll talk about the overall, I'll introduce the overall mathematical schema in a couple of slides now, and then I'll graphically show you how the algorithms work. And if you want some more detail, you just have to look at the papers like this one down the bottom left. Now, that's available on the webpage, or you can talk to me. So, that's the first strategy, and in order to make that effective, what we need is we need to define a measure of the difference between Q and P, these two distributions up here, and then we need to minimize it. So if we have a measure of that difference and we minimize it, that is an optimization problem. And that is exactly how this variational method works. So then there's a second strategy, and that is that we, instead of using the analytical form of Q explicitly, we represent it by a set of samples. But these are not samples that are just generated randomly from some distribution Q. We usually start with samples which are generated from our prior, and then we're going to move the samples to better represent P. And so Q here still exists, our what's called the variational family of functions. So up here, the Q is the Gaussian. Down here, the Q still exists, but it's represented by the samples themselves. So it's never ever explicitly written down. It is the distribution of the samples. So if we perturb the samples, we perturb Q. So how this will work graphically is we might start with our prior distribution shown up at the top. Let's just say we had a prior which was a Gaussian somewhere, and we take a few samples of the prior. So maybe we take these samples shown by arrows. And in this strategy, what we do is we only have the samples from now on, and we work out which direction we should perturb the samples in order to make them better represent the posterior. And in this case, it turns we've got to perturb them to the right, so we do so. And in a second iteration, we work out how we've got to perturb them, and we perturb them again. And we carry on doing that until the samples represent optimally the distribution P. Now, what's nice about this is that we have a very flexible parameterization of our distribution Q down the bottom there, because we never have to explicitly write it down. It's just represented by the samples. And so in the end, we have the samples, and we can simply we could histogram them in order to get an approximation for Q if we wanted it, or we can just use the samples themselves, but they will be optimized to best represent P. They'll not be constructed from random samples of a Monte Carlo process. But again, in this case, there is an implicit Q, an implicit sampling distribution. And in both of these strategies, what we need to do is to define this measure of difference between Q and P and then minimize it. And so the particular measure of difference we use in these variational methods, at least, is called the Kullback-Leibler divergence. And it measures the difference between any two distributions. It looks a bit complicated. It's written just like this on the left, KL divergence, we usually say. And it's the difference between distributions Q and P. So those two functions we had on the previous slide. And it's given by this function, this formula here, which is has expectations over the Q distribution of log of Q and log of P. And then it's got log of this thing here. Now remember, that was the evidence, P of D. So we're going to come back to that. Now the nice thing about this measure, the KL divergence, is that it's always greater than or equal to 0, and it only equals 0 when Q is equal to P. So that's the kind of measure we like for optimization problems. That means if we minimize the KL divergence, we're going to get a distribution that's very close to our posterior. Now that log of evidence term over there is problematic. We don't want to have to calculate that in order to measure the difference between our distributions. Otherwise we'll be here all year. So let's just rearrange this formula. We'll take the other two terms over to the other side of the equation. And we just leave the evidence on this side. Now, the reason we do this, if we look again at the evidence, we see it's constant with respect to Q. So as we change, remember, it's Q that we're changing to best represent our posterior. As we change Q, this right-hand side of the equation doesn't change at all. Now, what we want to do is to vary Q to minimize the difference between them, the KL divergence. But because the right-hand side is constant, that's equivalent to maximizing the sum of these two terms, or the difference between these two terms here. If we maximize the results of these two terms, because that's constant, we must minimize the KL divergence. And these two terms are much easier to calculate because they don't include the evidence at all. And so those two terms together have a special name. They're called the evidence lower bound. And that's because together they are always less than the evidence, because this is a positive or zero number. So they're called the elbow, the evidence lower bound. And our strategy in most or many variational methods is to maximize the elbow, maximize these two terms, because that automatically minimizes the KL divergence. So that's the same strategy for both of the two methods I've been talking about, or the two strategies. It's the same objective, is to maximize the elbow. And I'll show you how the first of the two methods works graphically, ADVI. So let's say in the top left, we have some posterior distribution that we don't know. It's a distribution over velocities, so the velocities are greater than 0, in this case, less than 5. But within that, we don't know what the distribution is. We want to estimate it. ADVI works by first transforming this bounded space from 0 to 5 into an unbounded space. Sorry, I'm pointing at the wrong screen. It goes from a bounded space from 0 to 5, top left. It transforms it using just a simple log transform into an unbounded space that goes across the whole real line. And there, we can approximate the posterior by a Gaussian. So now we can use a Gaussian approximation because that extends over the whole real line. We then standardize the Gaussian, which is just a standard operation in statistics, and then we fit the Gaussian to the posterior by minimizing KL divergence by maximizing the elbow, and then we transform back. And we don't know the red line here, that's what we're trying to estimate, but by this stage, the blue line gives a decent approximation to it. And that is our ADVI approximation. Now, the thing to note about ADVI, it's really quite simple. It's only a Gaussian. It's a simple log transform and then a simple log inverse transform here. And all we're doing is fitting a Gaussian in this log transform space. But that means that the disadvantage is we're not going to be able to fit very multimodal distributions with ADVI. It's a very simplified version of the uncertainty. It works in this nice graphical case, but it won't work in some others. But the nice thing is it is an optimization. So this is not a random sampling algorithm, it is an optimization algorithm. The second algorithm, remember, is the one that's based on samples, and then we optimize the samples. And so I'm going to represent that with this little graphical example. So here is the posterior distribution in blue now, that we don't know what that is. The prior is just Gaussian. And so we take some samples of the prior, and then we just histogram them here to show you where they are. And then we continually transform the samples using a very simple functional form like this, which is optimized again to maximize the elbow. And as we do that, and we just do it iteratively over and over again, after iteration, only 5 iterations, the samples have redistributed themselves to represent this shape. And after 500 iterations, they're giving a very good approximation to the posterior distribution. And again, the nice thing about this is it's purely optimization based. So we're maximizing the elbow. The second SVGD is actually quite nice to display graphically in 2D. So let's say that this is the 2D posterior, this blue shading that we don't know. The prior is just a Gaussian distribution. So we take a set of samples of the prior as shown here. And what's shown by the arrows for each sample is just the direction that we should perturb them to maximize the elbow. So there's a way to calculate those gradient directions. Again, if you want to know the details, just have a look at that paper or contact me. If we then, and there's a very nice little app on the web at this address that you can use to just show you the perturbations in the sample. And this is what happens to the samples as you go through the iterations. They self-organize to distribute around the posterior distribution. So in the end, you get a good sampling of the posterior, but it's definitely not a random sample. This is a self-organization of the samples to represent the posterior. And so ultimately, at the end of the convergence, they are optimally distributed such that their density is larger at the high probability areas and less at the low probability areas, and they represent the posterior. And just to contrast that with like a simple Monte Carlo algorithm, which is just a Markov chain, we're just stepping around in parameter space. What you can see here is that what you're going to end up with are a set of randomly distributed samples, and only as these become very, very numerous, like usually many thousands of samples, will the density of them really reflect the density of that background blue distribution. So let's see these in action quickly. A synthetic test. Let's say this is the true structure that we're trying to image. So a high velocity background and a low velocity anomaly. It's circular. And we're going to solve this on a grid that's much coarser than the one shown here, so that this structure actually lies outside of our parameterization. Nevertheless, we're going to try to estimate it. And we're going to use travel times between this set of receivers. So this will be inter-receiver travel times between every receiver pair. And we use them to try to invert for the structure. So let's put the real structure over there, and I'll just show you immediately the results that we get from ADVI. And here we have the mean of that algorithm. And what we can see is, again, we do nicely image the low velocity region in the mean. It's not got the same velocity as the true model, but it doesn't have to. This is a statistic of the family of models that fit the data. It's not actually a model itself. It's a statistic. Together, this one and the standard deviation on the right represent some measures of the spread of that family of models. So we've got this low velocity zone, and then we have a halo of low velocities around about it. And over in the standard deviation plot, we can see that we have higher standard deviations in the middle and also outside where we have no data, low standard deviations just around that, and then another halo of slightly higher standard deviations. And if you look carefully, we do actually have a very slight uncertainty loop there. So very slightly higher uncertainties on the outside than on the inside of that low velocity zone, but only just. Now that's a bit of a worry because we saw them quite clearly previously. The problem with Bayesian tests is that although we know the true model, we do not have any idea what the mean and the standard deviation should be. There are almost no problems where we know what the answer should be in Bayesian. So the only way to find out whether this looks correct or is likely to be correct or not is to try it with a completely different algorithm and see if you get the same answer. So let's now try it with the second of those algorithms, SVGD, and this is what we get. Now, if you look at the mean plot in the middle first, you can see the low velocities surrounded by the halo of low velocities again, slightly lower velocities. And if I just look back at ADVI, it very well matches the ADVI solution for the mean. But if we look at the standard deviation on the right, we see that SVGD, the sample-based algorithm, is giving us low uncertainties in the middle, surrounded by two halos of high uncertainties, a double halo. Now, we haven't seen that before. Remember, this is, okay, so let's leave it at that. We've got this double halo. So now we're fairly confident in the mean. We've seen that by two completely independent algorithms, but we don't know which of these uncertainties is correct. So now we've got to solve it by the third algorithm. So we just use that Metropolis-Hastings algorithm, the Monte Carlo one that I just showed you schematically in the movie, and we solve it with that. And now again, we get the same mean structure, and again, we get this double halo and uncertainty. And this is now a random sampling algorithm, it's completely independent from the other two. And we see a very similar type of structure as SVGD. So we're now pretty confident that this is the right structure. It may not be exactly the right values, but this double halo is correct. It is the right uncertainty distribution. And that means that ADVI really is not giving us a very good estimate of uncertainty. Now, we kind of expected that because it's got this Gaussian approximation, whereas the other two, SVGD and Metropolis-Hastings, don't. And so I think we've got a good grasp now on what the right solution is. Now, we also then applied the reversible jump Markov chain algorithm that I presented an hour ago. And this gives a very interesting result. It's completely different from the others. So the mean looks like a model. It looks like a good model that represents the true model. Uncertainties look like the ones we saw previously. Around the low velocity zone, we've got this very sharp boundary or halo of high uncertainties, and then very low, almost zero uncertainty outside of it. Now, this is really different. And you know, we've just said we're convinced this is the right solution. So what's going on with the reversible jump method? Well, this is where we realize that the different algorithms give very different results. We've seen that between ADVI and the SVGD and Monte Carlo. But here, this difference is coming not from a Gaussian approximation, it's coming from the fact that we used a very different parameterization of the models. We used Voronoi cells, whereas all the previous methods I just showed you were on a regular fixed grid. And these Voronoi cells, as you can see, some of them are quite large and they're constant velocity inside. Now that's quite strong prior information on every model. We're basically saying there is constant velocity in large patches across the model, and only models that look like that are valid models. So we've really injected a lot of prior information here. Let's return to that question of prior information earlier. And that is why we get a solution which, for a start, is far better constrained in the sense that the uncertainty is much lower because we really aren't considering all of the range of variation of models that we would get in regular cells. And secondly, it's why we've got such a sharp boundary, because we're considering large patches which have the same velocity. Now, we're lucky in this case because that's the true model, has large patches of similar velocity. But of course, in the real Earth, it doesn't look like that. And so this example is important because it shows that those reversible jump methods, if we use Voronoi cells, which a lot of people do, we're injecting prior information and we have to interpret the results on that basis. If that prior information is wrong, if it doesn't conform to the Earth, then we're going to get results which are wrong, or at least different. We have to interpret them differently. In this particular case, if we're looking for uncertainty in the image, of what we would regard as a regular image, so a regularly gridded image, this seems to be the right result from Metropolis Hastings and similarly from SVGD. Somewhere around those results seems to be the right thing. Just to sum up then, let's just look at the computational cost. Now, the Monte Carlo methods, so that Metropolis Hastings one, took 12 million simulations. The reversible jump method took 3 million, but that's come up with a very different solution. SVGD is the next cheapest, and that did reach a similar solution to the Markov chain at a substantially reduced cost. ADVI is the cheapest overall, but remember, it didn't give us a very good estimate of uncertainty. So in fact, those two middle methods are the ones that are giving us what we would regard as a reasonable uncertainty estimate of an image. And of the two, SVGD seems to be the better in terms of efficiency. Now let's just see how these work on real data. So this will be very quick and then I'll end. This is just an array of receivers on the ocean floor. This is about 5 kilometers across, 8 kilometers upwards, north-south. It's out in the North Sea, so it's on the seabed. And a few days of recordings of ambient noise. So we use that to convert the red receivers here into virtual sources, which were recorded by all the other receivers, and we then picked travel times between the red and every other blue, each red virtual source and every blue receiver. And that was our data set then to perform tomography exactly similarly across this array. We used ADVI, and here is the result. That's the mean model that we got and standard deviation on the right. And the mean structure has this sort of intriguing low velocity structure in the middle, a high velocity and a low velocity over there. Now at this point, we don't know whether this is the right solution, so we solve it again with a completely different method, SVGD, and we get this result. And we see that if we look at the mean structure, it's really quite similar between the two, and these are quite different methods. So now we're pretty confident in the mean. But again, the standard deviation is quite different because ADVI has this Gaussian approximation implicit, SVGD does not. So we wanted to solve it with a third method, but we know that the third method that matched SVGD previously was the Metropolis Hastings Monte Carlo. Unfortunately, in this problem, I mean, we saw previously that took 12 million iterations. In this problem, we couldn't even get it to converge. It's just too large a problem. We did run it with the reversible jump Monte Carlo method, and this is what we got. Of course, in this case, we know the uncertainties are very, very low here artificially because we've imposed these large areas with constant velocity in the prior. Nevertheless, if we look at the mean, we've still got this structure. It's much lower resolution in this case, again, because we're saying that large areas should be constant. But if we just compare it to the SVGD, I think that mean structure is, at least at the large scale, again, confirmed. So here we are. This is a real data example. The mean structure, I think we're pretty confident in now, is one of something like this from the SVGD. Our best estimate of the uncertainties is probably the SVGD. But we don't know because we don't have a fourth method to compare this to that can run in reasonable time. So that is the kind of state of the art currently in using these methods. Now, I do have an extra section on applying the same methods to full waveform inversion, but I think given the time, I want to just break out of this at this point. And if anyone's interested in that full waveform inversion method, they can look at that second paper by John 2020B and contact Jim or if you have any issues with that. So at that stage, I think I'd like to wrap up today's seminar. Thank you very much for a little bit of extra time there just to get through that first part of the variational methods. And tomorrow, as I say, we'll go on and we'll look at invertible neural networks and another variational method, normalizing flows, before we bring all this together as to interrogate the subsurface. I'll turn back to you now, Simon.
So today's session is going to be closed before closing some questions. If you have 1 or 2 questions, we can on this second part. First part of this session, some questions was there. 1, 2. So one question was from Gautami Das, that is there any role of testing different likelihood functions in reducing the curves of dimensionality?
Yeah. In principle, the likelihood function should be fixed by the data. I mean, the likelihood function is supposed to represent the fit of any model to the data, and that should be governed by the uncertainty distribution on the data. So it should really be measured and it should be parameterized like that. Now, the problem is that we often don't have very good estimates on what the uncertainties on data really are. We might assume they're Gaussian, but they're almost always not. We might assume they're uncorrelated, they're almost always not. So I think that's a good question. I can't say that I know of a lot of research on that, but I think it's a good question in the sense that there is flexibility to try different likelihood functions. Given that we don't actually know the data uncertainty distributions, we probably could try different likelihoods. So good question. I can't say I can point you to any research on that.
So there is another question by Aditya Sen. In multi-parameter forward FWI, can the proposed method tell us about the trade-offs between different model parameters being inverted?
Yes. So essentially what you end up with in the FWI, maybe I'll just show you a picture from the final result, in fact, just to explain. What you end up, actually, you're not seeing my screen, are you? Do you see the slides now?
Yes.
Yeah. So what you get out, is this working? Okay. So let me zip through this and I'll just show you a picture. Remember that what we want, come on, get there in a minute. Remember what we get out is this distribution of samples from SVGD at least, and they embody the correlation of the function. And indeed, even with ADVI, we get correlated results because they represent the results as a Gaussian or a transformed Gaussian, and that Gaussian has full covariance matrix if we want it to. So the answer is yes, we do, and I'll probably just show you some, just go straight to the results for the FWI. This is the FWI. So this is a true model. So this is on the left, we have the true model, and it's an elastic case where we've got a p velocity, a shear velocity, and a density. We've got some sources on the bottom, receivers on the top. So this is a transmission FWI problem. We record that data, and then we invert just the data to try to find an estimate in the model. And with SVGD, we get this middle column shows the means of all the samples, and the right column shows the standard deviation for p velocity, shear velocity, density. Now the p velocity is very poor here because these are essentially shear sources of shear energy dominantly. And so we get a very poor estimate of P velocity. But the fear velocity and the density, together with our uncertainties, make a lot of sense, particularly because exactly the same problem was solved by a different group using Hamiltonian Monte Carlo, and the results are really very, very similar. So, and the computational cost of these two methods was also similar, except that the SVGD is completely parallelizable. So we can distribute it across as many processes as we like, whereas Hamiltonian Monte Carlo is absolutely not parameterizable at the top level anyway, because each sample depends on the previous sample. And there's a particular mathematical property called detailed balance, which is broken if you distribute it. So there is an advantage to using SVGD, which if you have access to parallel machines. In terms of the correlation between parameters, I think I've got, I thought I had a movie here that showed the correlations, but anyway, that shows you the kind of results that we get from applying these methods to full waveform inversion.